Welcome to this talk on the assessment of existing structures. My name is Lily Erskine and I'll be your chair tonight. I work at a firm called Narrow in Edinburgh and I've got a decade of experience working with existing structures. Today's discussion launches a new mathematical approach to the analysis of existing structures. With aging infrastructure and an ever-growing necessity to reuse rather than demolish, the need for advanced techniques in assessing existing structures has never been more critical. Helpfully for me tonight, all our speakers are called Andrew. Joining us from Arup, Andrew Lawrence is a care accredited engineer specialising in existing buildings. Also from Arup is Andrew Smith, who forms part of Arup's specialist technology and research team. Last but not least is Andrew Rolfe from Mott MacDonald. He is a care accredited engineer with 27 years of experience working with existing buildings. I'll now hand you over to Andrew Lawrence, who's going to be our first speaker.
So, this tool is something that we've been developing with the iStruct over the past year, originally thinking about all the buildings which were going to need to be assessed under the Building Safety Act. But of course, recognizing that the reuse of existing buildings is really becoming much more important as well. I think we all know that existing structures often have a lower factor of safety than modern codes. There are many reasons for that. Just a few examples. Concrete, for example, in terms of shear resistance, fire resistance, not fully understood back in the 1960s. The Ronan Point report said that our wind codes at the time were outdated for taller structures. And we know that permissible stress codes that we used to use weren't so good at dealing with adverse and beneficial loads. So just a few of the reasons. But the question is, what factor of safety is actually acceptable for those existing structures? There is some quite limited guidance, but much of that guidance is conflicting. There is some new guidance coming out in the new part of Eurocode Naught, which is talks about accepting a lower reliability for existing structures. But of course, most of us as structural engineers are not reliability experts. And to be honest, we're much happier with, we're used to much more prescriptive guidance. So that was really what we were aiming for with this tool, was to create something which gave a consistent, much more objective approach, so that all of us as members of the institution could look at buildings and come up really with the same answer in terms of what would and wouldn't be acceptable. So I'm now going to hand over to Andrew Smith to talk about the details of the tool.
Great, thank you, Andrew. So thank you, Lily and Andrew, for the introduction. Yes, I will be taking us through the new tool that we've developed in conjunction with the iStruct. So first of all, I just wanted to give a bit of a background to the process of assessment, because it's really fed into our thinking of how to develop this tool. So as many of you will be aware, that there's lots of different approaches that we can take as engineers when we're trying to assess an existing structure. One of the most common ones is we might do calculations to historical standards, or we might reach to modern standards and do calculations based on those. A third one, we may also want to carry out load testing to directly demonstrate performance, or we might just take a more judgmental view based on past performance. Now, the first one of those, calculations based on historical standards, that's really useful for understanding whether the original design was carried out properly. Now, the second one, now this is the perhaps the preferred approach if you really want to understand a structure's actual factor of safety. And the reason for this is that modern standards are typically far more advanced than historical standards, and therefore they generally capture the physics and the underlying behavior of materials far better and far more precisely than those historical standards do. Which is why this is the best way to actually understand the real factor of safety. Now, load testing can be a very useful way in some circumstances, but in practice, it can be very difficult to do, requiring lots of temporary works, and it's often very expensive and disruptive if a building is already occupied. And finally, unfortunately, the last one, assessment based on past performance, it clearly past performance is a very useful indicator about the performance of a structure, but it doesn't really tell us how close something is to failure. So in the tool we've developed, that calculations based on modern standards is the method or the basis for the method that we're using. But it's very important to acknowledge, as Andrew said, that historical or existing structures typically won't comply with modern codes, and there's no actual requirement for them to. So instead, what the tool aims to do is it tries to provide a method for judging what factor of safety is really reasonable or appropriate for an existing structure. And really, to do this, we've set it out in terms of 3 steps. You know, we can carry out measurements, testing, analysis, things that really help us understand the structure as well as we could. Then the second step is we can try to reduce partial factors from the modern code values to ones more appropriate for assessment due to higher certainty. And then finally, we can take a step back, look at the overall utilization that we're getting at the end of those calculations. And instead of rejecting anything that's over 100% utilized, we can look at it in a more objective way and say, right, well, how serious really is it if we're slightly over 100%? And I'll go through each of those in more detail in this presentation. Now, before doing that, I just wanted to provide a little bit of a background or recap to partial factors. So typically the way that for modern limit state design, the way that we use factors, I'm sure you'll all be familiar with this, is to get our design loads, we factor up a representative load with a load factor, which in this case we've denoted as gamma F. And we say representative for live loads or for variable loads. That representative value will typically be a characteristic value, or an upper fifth percentile, one that has a 5% chance of being exceeded. For permanent loads or dead loads, then that will typically be a mean value. Now, on the strength side, our design strength is equal to some characteristic property, and we'll typically divide that by a material factor, which we call gamma M here. And here, the characteristic strength is a lower fifth percentile. Now, there are other ways provided in Eurocode, not for splitting up these factors or for calibrating them, but this is the simplest way that is used in most calculations. And then finally, we have a utilization, and we'll take our design loads and divide them by our design strengths and compare this to 100%. Now, when we're assessing existing structures, there are typically 2 arguments that are made for either reducing our partial factors or accepting a greater than 100% utilization. And those are that it's possible to obtain a much higher degree of certainty in those existing structures associated with the loads compared to during design. And secondly, it's often common to accept a slightly higher degree of probability of failure compared to a completely new build structure. And as Andrew said, that there is existing guidance around both of these and how we can adjust factors and utilizations, but unfortunately, that's a lot of this guidance is inconsistent or contradictory or incompatible between different sources, or the methods are very complex. So this brings us on to the overall purpose of the tool that we've been developing. These are the guiding principles that we've been using. So the overall aim is to provide a consistent approach for assessing the safety of existing structures. And we want this method to be safe. Clearly, we don't want to end up with assessments which are unsafe. We also want it to be simple to use. We don't want it to be overly complex or overly demanding. Another guiding principle that we've tried to follow is objectivity. We're trying to minimize the amount of subjectivity in the process as far as possible and provide as much guidance so that different engineers are likely to reach the same result. And then finally, we want it to be consistent with as much of that existing guidance as possible. So now onto an overview of the tool. As I mentioned before, there are really three steps that the tool is broken down to. The first one is measurements, testing, and analysis. And really, this boils down to pushing the structure as hard as we possibly can, making sure we properly understand it. Now, after that, once we're comfortable that we've understood it as best as we can, we'll hopefully have a higher degree of certainty of the loads applied and the strength of the structure compared to if we were doing a design. And so there's an opportunity to reduce those safety factors. In effect, we're trying to target the same probability of failure as would have been expected in design. And then finally, the third step is reviewing the overutilization if we're still over 100% using those reduced factors. And it, 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 it's important to say this when any acceptance of a higher probability of failure um, is captured in this final review of the overutilization step. So what we're going to do is we're going to go through each one of those in turn in slightly more detail. So step one, measurements, testing, and analysis. As I said before, this is really about pushing the structure as hard as possible. And in the upcoming guidance, we're not going to cover this in a significant amount of detail. There is a lot of guidance documents about how you can measure actual loads in a building, what are appropriate levels of measurements you should take for geometry or densities, how many cores you should carry out, how to carry out those statistical calculations. There's lots of guidance that's available, so we don't want to duplicate that. For example, the iStruct's appraisal of existing structures guide. So then moving on to step two, which is where the method really comes into play. This is where we're trying to reduce our safety factors to account for our greater certainty in loads and strength. Now, at, at this point, it's useful for us to take a step back and think about, what's the real purpose of safety factors? And effectively, that they are really there to account for uncertainty and variability in design and construction. And that this could be due to all sorts of things. It could be due to dimensional sizes of elements. It could be due to variations in densities, um, lack of predictability of loadings, strengths of certain materials, simplifications we've made in the modeling. There's lots of sources of uncertainty and variability in structural engineering that the partial safety factors capture. And in general, if we've got a higher degree of uncertainty, then as a result, we will have higher safety factors to account for that. Now, if we compare design to assessment, in design, we're dealing with something that hasn't been built yet. Whereas when we get to the assessment stage, the structure's already there, and there's an opportunity for us to go and really try to understand it as best as we can. And so compared to design, there's much more of an opportunity to reduce the level of uncertainty. And so as a result, if we compare the design scenario to the assessment scenario, we can see that for design we might expect higher safety factors, and for assessment, if we've done lots of investigations and we really properly understand our structure, then there should be an opportunity to reduce those safety factors. And that's what the tool that we're providing gives guidance on. So I mentioned some of these briefly earlier, but what are the sources of uncertainty that safety factors try to account for? Well, this is a diagram that's provided in the older version of Eurocode Naught. And it highlights an important thing. It shows that for both loads and strengths, the partial factors are the overall partial factors, which are on the left, we've got like gamma F for loads and gamma M for strengths. They can sort of be broken down into each down into two parts. There's one part which is about uncertainty in the actions themselves or in the material properties themselves. But then there's also for both of them this component that is called the model uncertainty, and that's really down to the simplifications in our analysis methods and how well we can model the actions themselves or the effects of actions. Now, unpacking that a bit further, what we've done in the tool is we've tried to break that down a bit further into a number of different categories. So for loads, we've broken that down into dimensional uncertainties or density uncertainties, and those two will typically be very relevant for permanent loads. We've got lack of predictability of variable loading, that's the third category. Then there's a level of uncertainty with indeterminacy of structures, and this is when we're looking at effects of actions. We often don't know the exact effects of those actions inside our structure. Then when we're doing design, there might be modeling simplifications. We might ignore some second order effects if we're within certain limits. And then finally, there's always going to be just a general degree of variability and uncertainty in these existing structures. So what we've done is we've taken the partial safety factors and we've broken each one of those down according to these different categories. So, for example, if we take a standard permanent loading factor of 1.35, uh, in a rather simple way, we can take that and break it down into a 1.0 and the 0.35, the bit above one, and we've taken that and broken it down into these various various different components, and we've assigned weights to each of those different components. And I've drawn them diagrammatically here in this pie chart, but the tool when it's published will provide far more detail about the relative weightings for these. Now, in order to come up with these weightings, what we've done is we've taken a look at a wide range of industry guidance documents, which already recommend different reductions in different circumstances associated with different um, levels of greater certainty. And we've used them to try to calibrate each of these weightings. Now, what the method then does is it then says, all right, well, these components are intended for design. But in assessment, you can gain more certainty about the dimensions. So it says if you've done this amount of measurements or this you have this degree of certainty about your dimensions, here's how much you can reduce that component of the partial factor for. And you'll go through each of these different components and see how much you can logically reduce that component based on your level of knowledge with the structure. And so once you go through the method, what you'll be able to do is say, well, we're going to start with 1.35. That's the value from the unreduced value appropriate to this situation. And then we'll say, right, well, we'll look at dimensions, look at densities. And in the end, you might end up with a number, say, of 1.2 or 1.15, depending on how much knowledge you have on your structure. What we've done is we've done this breakdown for lots of the typical factors that you would encounter. So, for example, here we've done it for variable loads and assign it to these relative weightings. And we've also done this for strengths. So here's the typical things that the strength factor might account for, and there's lots of things associated with the material strength, and then some things associated with the modelling or how you might or our simplified models for calculating the strengths of members. So, as an example, here we've got one for concrete where we're breaking it down into the different components. And one thing I'll just highlight is that for each of these, we've assigned a weighting to the category that we've called the baseline uncertainty. Effectively, this represents an amount of the partial factor that we don't that really shouldn't be reduced below. You can gain lots of information about material strength, or failure modes or geometry, but at some point there will always be a lower bound to the factors that you can't reduce them below to ensure a minimum level of safety in these structures. And here's another example for concrete reinforcement. So as I said, these weightings and the guidance on when you're able to reduce them, these have been calibrated based on a wide range of different um, industry guidance documents. I've listed some of them here. So finally, step 3. This is when we want to we've reduced the factors, we've understood the structures as best as we possibly can, and we're faced with the question: well, if we're still over 100% utilization, eh, how serious really is that? So to unpack this slightly, if we think about a 100% utilization, we can think about that as corresponding roughly to a certain probability of failure within a given time period. Now, typically codes tell us that 100% factored utilization, that's comparing the factored design values to the factored strengths, that relates to an annual probability of failure of roughly 10 to the minus 5 to 10 to the minus 6. And obviously, if we look at a longer time period, then the probability of failure goes up. So if we look at it over a 50-year period, which is what codes typically look at, or often look at, we might end up with a probability of failure of, say, 10 to the minus 4. And this is for standard design scenarios. Now, typically, instead of referring to those probabilities of failure, we actually refer to something called the reliability index, which is denoted by the symbol beta. And here you can see I've copied table C1 from the older version of Eurocode Naught. And really, the probabilities of failure are related directly to this reliability index beta by the cumulative distribution function of the normal distribution. But we don't typically need to worry too much about this relationship. Effectively, if we have a high beta value, that's a high reliability, then we have a low probability of failure. And if we have a low beta value, then that corresponds to a higher probability of failure. So if we're looking at utilizations that are over 100%, then instead of looking at the probabilities of failure, we would typically want to look at these reliability indices because they're a bit easier to work with. And we would expect those values on the right to be less than 3.8 because the overutilization suggests that there would be a higher probability of failure, so a lower reliability index. And effectively, the tool provides a simplified method that allows engineers to calculate these values. Now, when we're carrying out this part of the assessment, really there are two questions that that need to be answered. So the first one is, what actually is that reliability index if we've got a utilization greater than 100%? Now, answering this accurately is actually a very complex question and would require lots of advanced statistical analysis that wouldn't really be practical or proportionate on a typical existing building or existing structure assessment project. But what we've done is we've carried out um, a broad parametric analysis to derive this simplified equation, which engineers can use to approximately or to estimate the beta or the reliability index if we've got a utilization that's greater than 100%. So this helps us answer that first question and predict what the reliability index is. And you can see that it depends on that utilization. On the bottom of the fraction, we've got the two partial factors, our load partial factor and our material partial factor. Now, the second question is we've calculated our reliability index, but what reliability index is really acceptable? And this depends on a lot of factors, and this is where the engineer's experience and judgment really comes into play. Now, to help engineers assess this, we've produced a chart that will allow engineers to try to better understand the level of risk associated with with that reliability index they've calculated. So to step through this, clearly the acceptability of a utilization greater than 100%, or the reliability index that we've calculated, that depends on the beta value. So that's there on the x-axis. And what you can see is that as this, we've removed the values from this chart because it's still under review. But as you go to the right of this chart, beta goes down. So as beta goes down, then we end up finding that you're getting a higher and higher risk. Now the collapse area, that's there on the y-axis. And what this is trying to say is that as the collapse area gets larger, as the impact of the failure increases, then we need to be more and more careful about accepting a lower reliability index. And that's why we've got these sloping lines within the chart over here. And effectively, collapse area it's really a proxy for the number of people affected. But to try to keep the method simple, we're using collapse area. Now, another thing we'll want to consider is the actual accuracy of those calculations we've carried out. And in order to inform this, we've provided a suggested, we've called it the minimum uncertainty ring. What this is saying is that all of the calculations we carry out have approximations in them. And this tool is no different. So engineers need to think about how accurate their calculations really are, how much confidence they have in them, and decide once they've plotted their point on this graph based on the reliability index and the collapse area, how certain they are of that. Once you've gone through those three, you will end up with a point on this chart. So you may find yourself in one of these like high risk regions, moderate risk regions, low risk regions. It will depend on the exact calculation you're doing. But once you've figured out where you are, then deciding whether that risk is acceptable depends on things, for example, like the client's balance of cost, risk, disruption. And those are the sorts of things that as engineers we typically can't make a call on, but we need to make sure that the client properly understands the level of risk so that they can make an informed decision. And finally, that this isn't an exhaustive list. There's things like how ductile the failure mode is. Would there be any warning signs? Lots of other things. And when you're using this method, we would recommend that the logic for why a certain risk has been accepted or not accepted, and the steps that are being considered to reduce it, that logic needs to be really clearly documented. And it could be documented in a safety case methodology. For example, if you're carrying out this assessment as part of a building safety case assessment in the UK under the Building Safety Act, or you might record the thinking under an ALARP framework, and that there's lots of guidance about these available through the iStruct. So, coming on to a few conclusions. First of all, as I said at the start, the tool we've broken it down into three main steps. That first one, pushing the structure as hard as possible, then trying to reduce safety factors as much as is sensible, depending on the level of certainty we have about that structure. And then finally, reviewing that overutilization. Now, the tool is currently being reviewed by a panel of 30 experts from across industry and academia, and we're targeting a publication in autumn 2024. So the values you've seen in these slides, they may well change, but we wanted to launch it ahead of that to make the industry aware that it's coming. And I'd like to close on a word of warning. It, we really need to take caution when we start playing around with these reduced safety factors or accepting overutilizations. And the real purpose of this tool is to help engineers understand the implications of reducing those safety factors or accepting those overutilizations. Obviously, it's really important that an engineer understands the assumptions that are baked into this tool that we've developed and its limitations, and those will both be set out in detail in the upcoming guidance. And finally, clearly, this method or any method cannot capture gross errors in analysis or gross errors in the construction of the building that we're assessing that we're not aware of. So as engineers, we really need to make sure that we effectively understand the methods we're using and the tools we're using. So thank you for listening. And I'm now going to hand over to Andrew Rolfe.
Okay, hi everybody. So I have and thank you, Andrews. I have the unusual job of kind of providing an initial response to the tool as I've reviewed it. So the purpose of the next 10 minutes is just to give that overview as I've reviewed the tool and see how we could use it in anger and in application. So I'm just going to talk a little bit about why we're focusing on existing buildings, why we assess the buildings, the approach to assessment, the application of the tool, the importance of the tool, and my final thoughts. So as Andrew Lawrence mentioned, there's a number of reasons why we might appraise existing buildings. And obviously a key focus at the moment is one around sustainability. And we continue to build at a significant rate. And despite the calls to control our emissions, we have continued to increase the use of our natural materials, not decrease it. And certainly as a construction industry, we're responsible for around 50% of extracted materials. So we need to change. And as the kind of carbon hierarchy shows us, building nothing is one of the biggest impacts we can have. So the emphasis on building reuse is going to become more and more prominent in the next few years. So actually understanding our component parts of buildings and how they can adapt is going to become ever more important. But in the backdrop of that, we've also got a huge problem with the aging building stock, and particularly in the UK. I work a lot in the healthcare sector in the UK, and the graph that I've shown on here is just an extract from the ERIC data, which highlights the aging population of our buildings just in the healthcare sector, with over 40% of them over 40 years old. And a similar story exists in the residential market and the non-residential market, with significant percentages being built before the 1970s. So going back to the point that Andrew Smith made around the changes in the way that we design buildings and the assumptions that were made, we are looking at buildings which were designed in a different area. But we also have a problem with poor maintenance and the lack of investment in our buildings. We have a huge issue with backlog maintenance, particularly in healthcare, and that has a detrimental effect on our building materials and the way that we can reuse those buildings. So we need to continue to appraise these existing buildings. And as a result of that aging building stock is that the materials and those design practices that they were constructed from are historic, as I mentioned, and systems such as RAC or LPS systems have highlighted the need to better understand how building products were used and their limitations, as well as the impact that the age and the environment will have on these materials. So the nature of our appraisals will become more complicated, and we're likely to be facing more challenges around overutilization. And as Andrew Lawrence mentioned, we now have a new legislative framework to act against, and hopefully everyone is aware of the Building Safety Act. And it places new legal requirements, particularly around high-risk buildings, to understand our buildings better, with a particular focus on safety and risk. So typically why we asked as engineers to appraise buildings, and this is my kind of five thoughts around that. So whether we're adapting buildings, so the adaptation, so changing the plan or undertaking alterations, so actually knocking holes for buildings but not changing the use. I think extensions have become more and more prominent, so actually increasing the building size or perhaps adding stories to existing buildings. The durability, so fixing problems that are found or suspected, or even systematic problems that we're aware of as we've understood more about the building products, particularly around those 1960s, 70s buildings. whether a building's being converted, so changing the use of a building, so perhaps an office to residential or residential to something else. But also the resilience of our buildings. So as our buildings have to adapt for climate change, so as we're starting to do things like overcladding our buildings or changing the way in which our buildings operate from an environmental sense and the impact that they may have on our buildings. Sorry. So typically, I'm sure everyone is aware of the process for appraising existing buildings in line with the appraisal of existing structures. So this is my very simplified diagram that I tend to put in most of my reports, and this kind of breaks it down into a series of stages. And I think the tool itself really focuses on that assessment stage. So we've done everything else. We've done the desk studies and we visually appraised the building, and we may have undertaken some intrusive works, and we may have tried to understand the constituent materials. But actually what we've found is we've got to stage 6 and we're actually assessing the building elements and consider the implications of overutilization of those constituent elements. And at this assessment stage, this is where, as Andrew Smith said, we're starting to kind of pull those levers around loading or materials or factors of safety. So for me, as was mentioned, the idea that actually the first thing we do, we might look at the loading, we might try and understand what that change of use or that adaptation may mean, or how that space has actually been used as opposed to theoretically, or what the design intent may have been. So actually understanding what the true occupancy or dynamics may be, the actual fit out or the actual ceiling and services, and how we practically go about understanding that, working with our clients to articulate our assumptions. But this is very much a mathematical exercise or numerical exercise, as well as building that evidence base. But also the materials, so as mentioned, so actually understanding the specifications or the materials used in the design intent, the codes of practice or the specifications at the time. And we have knowledge of those existing buildings, and the appraisal of existing structures gives some really good guidance, as well as other contemporary sources give guidance around what we may expect our buildings to be made out of and the type of materials. But we can also sample these on site, as Andrew Smith mentioned, and undertake those detailed assessments of materials. And then finally, I suppose the purpose of the tool is really to understand what factors of safety we're looking at. And this is where I think there's always been quite a challenge. So these are codified allowances that we're normally looking at. And I think personally, as an engineer, we always find it slightly hard to kind of adapt and play with when we're undertaking appraisals. We know that we're changing the risk profile. We know that we're looking at factors of safety, but how much can we move this lever in order to really understand our building? So I suppose this is where I think that assessment stage expands out. So this is my slightly expanded version of that stage 6. So when we undertake our initial calculations, our initial assessment, and we find that something is overutilized, and therefore we might have to look at reducing loads and the implication of that. But actually, if that yields good results, and it turns out that actually the members themselves aren't overutilized once we've pulled that lever, then actually we might not need to go any further. But if it does show that we are overutilized, then that's where we might start looking at materials, and we might start trying to understand more about the materials that our buildings are made out of. And again, if both of those levers show that actually our elements aren't yet overutilized, then we just need to document those assumptions and maybe not move any further. But I think the purpose of this tool and the usefulness of this tool is once all else has failed, once we're actually finding a structure that, despite our calculations, show it's overutilized, this is how we may be able to work through this and understand the risk-based approach of what that overutilization means. And I think why I personally find this really important, so I've done a lot of work in RAC over the last several years now, and actually the recent guidance by the IStruct-D provided that unified approach to risk assessment of RAC. And I think having a unified approach to any sort of assessment is beneficial. It means that we can all use the same guidance as engineers, and we can benefit from that unified guidance when we're actually talking to our clients, because actually we're all singing off the same hymn sheet. We're all articulating the same similar measures of risk. So I think that personally, I think the exciting thing about this tool is the fact that it gives us this methodology for quantifying based on calculation approach, the potential risk, and providing that 50-year reliability index mapped against the potential consequences has great potential, particularly when we're actually articulating that message to our client base. And I think that's where I'm really interested, because this starts to give a data-driven approach to moving those factors of safety and understanding the risks and associated challenges that we're placing on ourselves. So hopefully making structural appraisal findings less subjective and more focused on that evidence and calculation base. And also, I think it will allow us to articulate that risk profile better, considering how the appraisal or adaptation that we're undertaking will really impact on how we articulate that message. So this will provide guidance on those implications. So how that adaptation that we intend to make will affect the structure, what elements are overutilized, the degradation that we've witnessed, or the system limitations we're aware of, and the level of detail that will allow us to describe our findings in terms of an ALARP framework or a risk-based framework to our clients, and really highlight the limitations that their building may have. So in terms of my final thoughts, I think refurbishment and retrofitting of existing buildings is going to be key for us to have a sustainable construction industry. So it's going to become ever more important. I think particularly with the HRB, so the new legislative framework around Building Safety Act, we're going to have greater understanding of our buildings and their components and the factors of safety that they are working under. And I think the tool is just one of several levers we can pull when we're appraising existing buildings, but I think it gives that fantastic unified approach that will be beneficial to appraisal going forward. And I think the ability to give data-driven insights is always useful when we're driving better discussions with building owners. So thank you. I'm now going to hand back to Lily, who will field questions.
Hello, everyone. Thank you for that, guys. I think it's quite clearly an interesting new approach. The thing that I can see being quite critical, having listened to you, is ensuring a responsible level of communication as a building is handed to others, kind of other owners, other custodians, as it moves through its life, if its life is then extended for the next 100 years. And how that communication is managed I kind of see as a vital next step as part of this. Do we need to legislate to that effect? I'm going to move to the questions that have come in from the floor, of which there have been quite a few. So I think the key one initially is from Katrina, which is BRE warned against reducing partial safety factors in 2012. Why are we now pushing it? And what is to stop another engineer pinching an inch in 15 to 20 years? Where are we drawing the line on safety?
I'm happy to try and answer that. I think it goes back to the word of caution that Andrew Smith has just said. This reducing the factors, for example, because we have a little bit of material strength testing, it's not to be done superficially. We really need to have a very accurate view of our structure, be it the dimensions or the loads or the strengths or whatever, in order to take advantage of these reductions. It's not so I know we refer to this as a tool, but this is simply a way of some quantification that goes alongside some very, very thorough assessment of the existing structure, and to try and quantify things rather than it being based too much on judgment.
Andrew, Rolf, have you got anything else to add? Or
All I was going to add is I think that just to build on that, I do think this is just one of a number of tools, and I completely agree that there is that word of caution. I think for me, the ability to take out that kind of subjectivity or the kind of reliance on the kind of the fact that a building has stood there for a very long time and therefore it's okay. I think the ability to, like, we should always assess our existing buildings with the rigor that that Andrew Lawrence describes. And actually, I think this gives another layer to that rigor of actually understanding once we've been through that appraisal process, that this actually gives us an understanding of when all else fails, what utilization do we think the structure is acting under. So I think it's not just about trying to eke more out of a structure in my mind. It's actually about better understanding how a structure is working.
Fantastic, thank you. Next question from Sam Patterson. Are historic materials manufactured under different standards and conditions compatible with modern Eurocode-based material factors?
I'm happy to chime in on this one. I think the modern Eurocode safety factors are obviously written for modern materials, and there will be some up to some point in the past for different materials those will be applicable, and then for historical or heritage materials there will be much greater degrees of, for example, variability inherent in those, and those so in many scenarios, no, the Eurocode factors aren't appropriate, and other factors that are provided by other pieces of guidance are more appropriate. Now, one thing I just want to add in here is that when the tool is launched initially, it will, on the material side, it will cover reinforced concrete, relatively modern reinforced concrete, and steel. But there is an aspiration and works ongoing to add in many more materials that you typically find in heritage structures down the line.
I asked a very similar question to that one when we went through it yesterday. So I think there are a few questions that sort of ask the same thing here. So I'll try and combine them. One is if the building is still standing and working with no obvious distress, does that mean that we're just looking at it in the wrong way? Do we need to go down this route?
I mean, personally, I would say, I think one of the challenges sometimes in that instance is that building may be working and not showing any signs of distress, but may be existing with a very low factor of safety that we may not understand. So there's always the assumption that because something is stood there, it is perfectly fine. It just may not be stood there with the same level of factor of safety against failure that we would normally expect within an existing or within a modern designed building. Yeah, that would always be my argument. Yeah.
There are some questions here about the diagram that you had with the different colours, the risk factor diagram, and whether or not that will be provided with the tool, and some commentary around that it doesn't appear very quick and easy.
Yeah, so firstly, on the chart, that will be provided with the tool with the actual numbers on it. The reason we've removed those numbers is just because it is currently under review. And to quickly tackle another question, I mentioned it's being reviewed by 30 people from industry and academia. The vast majority of those are practicing engineers, very experienced in assessing existing buildings, working in real practice. That is the vast majority of those reviewers. Going to the second part of your question then about the ease of use. Clearly, there are steps involved in this tool. We have tried to make it as easy to use as possible and as consistent as possible, but we appreciate that there may be additional steps required compared to some other current approaches that are adopted. That the main purpose of this is to try to bring together lots of different competing and slightly incompatible bits of guidance and advice so that overall we can push structures harder than we're able to at the moment. Hopefully that answers the question.
Just scanning through the questions here. We've answered quite a few of them. So a question from Ian Dorman. He says, I appreciate it was mentioned that collection of data to inform assessment is a wide topic. Assuming, though, that little information is available to inform the desks from the desk study collection of data, the intrusive testing becomes key. This appears to present a challenge, particularly assuming the building is assessed is being assessed may be occupied. Is there a plan to include guidance in the tool around the amount of representative data needed to reliably inform assessment?
Yes, there is. The tool will provide clear guidance for how much information you need from, whether that be from desk studies or from intrusive investigations, in order to carry out that assessment. Clearly, at some point, if you know very, very little about your structure, then you're not necessarily able to do many meaningful calculations at all. And I would note that the additional guidance on that will be provided in guidance surrounding how the structural safety of buildings should be assessed as part of building safety cases in the UK, and that will provide methodologies for considering risks and carrying out those risk assessments.
Another person in the audience asked whether or not the total collapse area is per floor or in total, and how that correlates with the consequence requirements in the ALUP triangle.
Yeah, so this is total collapse area added up across all the floors. That's the intention here, and that's because it's intending to be effectively a metric for the number of persons affected by that failure or collapse. And clearly a larger collapse over a larger area affects typically a larger number of people. Now, in the development of the tool, we have assumed this is for normal occupancy levels, and some additional guidance will be provided about structures that have very high occupancy levels or might not fit into those typical levels.
And could you let everybody know what format the tool is going to turn up in?
Yeah, the tool will be initially in a PDF format available via the iStructEase website. I don't know if physical copies will be available, but yeah, those will mostly be in a report format. Now that it will be relatively easy to take the information that's in this document and put it into a spreadsheet. We've stayed away from doing that, or stayed away from providing one of those spreadsheets, because we think it's really important that when carrying out the assessment, the engineer doesn't view it as just a plugging numbers in a spreadsheet exercise, that we view this as one where we really need to understand the structure and the approach, and really needs to dig down into the information that's provided in that document. So that's why it's provided in that format.
And what do you see the next steps of this being? You've put it out into the world. Where does it go next?
Well, as I mentioned earlier, when it's put out, it will naturally be limited in terms of material scope. I think one of the key things we're excited about is making sure that this is applicable to a wider range of materials. That's a similar approach that you might get on, say, carbon assessment tools, where the range of materials you initially can cover in the tool is initially limited, and then you grow it as the tool is used more.
I think it's going to be important to. This is a journey for, I think, all of us as members of the institution. This is trying to move us from a position of a sort of a slightly binary position of where sometimes judgment is used without any quantification at all, to sometimes the hard sort of we need to comply with modern codes even if it's an existing building. So this is I think we're all on a journey as structural engineers in terms of working through and reaching a consensus on what is acceptable for existing structures. So I think the next stage is really the sort of the feedback and those sort of developing discussions amongst members. The and going on that journey.
There's a question here that asks, how are you going to account for fatigue and creep damages in the existing structure?
So the tool is initially aimed at standard calculations where those typically won't be that important for day-to-day assessments. Now, that said, the tool is applicable to any calculation that you may try to carry out. And so if you were to do a creep calculation, there will inevitably be some factors in that. Also, a fatigue calculation, there will inevitably be factors in that. And guidance will be provided on exactly how to use the tool in those circumstances.
And I think there are quite a few questions here around how the tool has been verified, who you've asked, how you chose the panel, how you've managed to kind of validate what you're putting forward. Could you talk perhaps a little about that?
Yeah, absolutely. So I touched a bit on in the presentation about, really at the heart of a lot of this is calibration. I said a lot of those breakdowns of weightings, it's really based on a lot of existing guidance and documentation that exists in industry documents. So in effect, a lot of these reductions and breakdowns are not necessarily completely new. They've just been collated in a consistent format and adjusted so they're compatible. On that third step with the colorful graph, although I didn't go through it in the presentation, there was also a detailed calibration exercise that's gone on with that graph to try to calibrate different points and where the acceptable and unacceptable and different risk zones go. And the details of that calibration exercise will be set out in the guidance documents. People can read that for themselves. Finally, on the reviewing side, as I said, we've got a large range of practicing engineers, and those aren't all from the same company. That is one person, or generally from lots of different companies. We're trying to get as wide a range of perspectives as possible, and the iStruct is leading on that reviewing process. In general, the reviewers fall into three categories. That there are people who are reviewing the method from a more procedural side. There are reviewers who are tasked with applying it on real world projects and comparing the results. And as I said, there are academics who are going through the more theoretical reliability side of it to cover all angles. And the thing, as I said at the end of the presentation, the thing I will note is that this process is ongoing, and we have presented some things in here. It is subject to change depending on the outcomes of that review process. So, just to highlight that.
Brilliant. I think we have covered pretty much everything that everybody has asked. All right. So I think first thing to say is thank you, everyone. I think we've heard tonight the outline of a new approach that might close the gap in the Eurocodes that certainly I see that exists. The bit that says the code says it should have fallen down 50 years ago and actually it's standing fine. And possibly this answers that question. Lots of people in the audience have asked about the application of this approach and how it can be used safely, although I think possibly a more consistent tool as put forward here tonight might offer something more reliable, more safe than those currently available to us, which are largely subjective. I'm sure I speak for everyone when I say I look forward to reading the final study when it launches later this year.